example now and calculate the effective shear stress in this channel. We're going to stick with this channel as we work our way to bed and suspended load transport. So we have this channel 5 meters deep, that's pretty deep now, and it has a velocity of 2.35 meters per second. We have some particles down here in the bed. The specific weight is 2.65 and the D50 is 0.2 millimeters. The first constraint, as we said, is to make sure that we have a Reynolds number greater than 70 down here in our lower layer. So we said that U star is the square root of G R S. Now, in our case, we have a slope of 0.001 meters per meter, let's call it. R is our hydraulic radius, and G we know. Ks, we said it can be from the range to 10 to 100 D50. In our case, we have a pretty flat bed, so let's use our Ks as 10 D50. And then our kinematic viscosity, we know that is constant 1 exponent -6 meters squared per second. So we're going to try and plug all this in, see if we satisfy our constraint. I'm gonna omit units here for R. What is R? Would be our area. 5 times we don't have a, let's say we have a 20 meters long channel, and our hydraulic radius would be 5 times 20 divided by 20 plus 2 times 5, and then our slope is 0.001. Then we have our roughness here, which is 10 times our D50, which is that quantity in meters, divided by 1 exponent -6, which is our viscosity. So if we calculate this, we get, let's try to do it in a calculator. I'm going to start with the hydraulic radius. I get a value of 361, so that is bigger than 70. So we can go ahead and utilize the more complex shear stress equations that we mentioned. Since we satisfied the first constraint, we're going to go ahead and calculate the effective shear stress, which is Dv prime equals 1/2 times the density of water. We know that it's 1,000 kilograms per meter cubed. Multiply this times this huge, crazy factor here, which is basically the logarithm of 12 times the depth. It's 5 meters in our channel. We divide it by 2.5 times our D50, we know it's 0.00002 meters. And then we enclose that, we square it, we multiply then by our velocity square, which is 2.35 meters per second, square it. Huge long way to calculate effective shear stress, but it is worth it. It comes out to 6
13.42 newtons per meter squared. And that is that. You follow the same procedure for the total shear stress, but remember to change this 2.5 to 100. And if you do that, you get a total shear stress of 13.7 newtons per meter squared. These two quantities will be crucial as we advance through our bed load transport formulas.